just a rendition of that. You can prove this also by Fourier series expansion or generalized Fourier series expansion.
So, why isn't the Fn and Fn prime inside the imaginary part?
Oh, they're all real, right? No, not they're real. When you take this and take this, this is common to both factors. This numerator is common to both of them. Okay, they're common to both of them. So the only thing that you need to subtract is the term that is not common to both of them, this term over here. So when you subtract this to that, it's like taking the imaginary part of that. Okay? So it's not because this is real, this is complex. But when you put the two terms side by side, okay, only the terms that are not common to both has to be subtracted. Maybe I did it a little bit too fast. Okay.
So inside of A, the K0 can also be complex?
Yeah, K0 is complex here. This is complex, this is complex. This expression is just obtained by this expression, which becomes this expression, which becomes this one. This is this, but I did not use this imaginary operator to get that. To get that, I actually find the expansion for this, which is given by that. Find the expansion for this, which is given by that. And the numerator is common to both. Okay. Common to both. The denominator is not common to both. So when we take the denominator not common to both and subtract them, I get this expression. Okay. Sorry, I did that a little bit too fast.
Sorry, one more question. Is the 2 important in A? Why we have a 2 here?
Because it's take a function and subtract it by its complex conjugate, you get twice the imaginary.
Yeah, but is the 2 important to have it? Because A is non-physical, as you said. It can be
A comes out of the mathematics, right? Comes out of the mathematics.
But we want A to be Hermitian.
A is Hermitian.
If A is
Hermitian.
No, we want A to be Hermitian.
A is Hermitian. So it must have real eigenvalues. There's one thing we know.
So will the 2 factor whether A is Hermitian
You
or
will,
not?
you will see later on that A in fact does have real eigenvalues. So this fact is not violated. A is Hermitian, it should have real eigenvalues, and then you will find that it does have real eigenvalues.
So, but if I multiply by half of I in front of G minus G Hermitian, I will get rid of that factor.
That's right, you get rid of that factor. I'm just taking this definition from quantum transport books. Okay, that's what they do there. They have a, not the dialectic Green function, but the Green function for Schrodinger equation. And they define the spectral function to be this. I don't know why. They never give any physical explanation. The physical explanation is mine. I just think about why they're doing this. They want to have a system that is Hermitian, a system that eventually gives rise to a time harmonic oscillating system that does not decay with time. So this system will provide that. So it's like you will have this Green's function, just scalar Green's function. If you take its real part, you get this, and then you take its imaginary part, you get that. The real part has singularity. And this Green function is actually produced by a singularity, a delta function source. The imaginary part, if you think of this as a removable singularity, there's no singularity. So this imaginary part corresponds to no source. Okay, no source form. But what is it due to? It's due to a wave traveling out to infinity and a wave coming back as a standing wave. Okay? It's actually the resonant mode of the system, you can think of it that way. Because it's a resonant mode of the system, it needs no source excitation. You can put in a source in this cavity that produces this mode, and you can slowly shrink the source, the point source, and take it away. This term will still persist as a resonant solution. It's always there. Okay? Same thing here. That this has a singularity, this has a singularity, but this thing in totality has no singularity. Which means that this spectra of Green's function solution is produced by a resonant solution. You don't need to point, you can put a point source there to begin with, you can slowly remove the point source, and this solution will still be there, resonating. Okay, that's correct.
Is this analogous to when we were talking about multiple method, like taking the regular part of these functions?
Yeah, that one is different. That one is when we're converting a spherical Hankel function to a spherical Basel function, take the regular part. This one is like taking the regular part. But that part was primarily mathematical, but I'm trying to extract physical meaning to this spectral Green's function. Okay? And that's what it means physically. And if you have some laws, quite interesting too, if you have some laws, then you will have something like this. If you take this imaginary part, you will have this lossy form, cosine k prime r plus sine k prime r kind of thing. And there is some decay away from the source point. But then there's this imaginary part that is always in time harmonic oscillations, even when there's loss. That's what it means. That is, if you have a lossy system, if you augment this with a wave that comes from infinity, you can set up the thing to be always in time harmonic oscillation. And hence you can quantize the system. So if you take this imaginary part, it comes up to be something quite interesting. Let me assume a tiny amount of loss first, because K naught is not pure real. Okay, K naught is not pure real. If I introduce a tiny amount of loss, that would be it. And then I can do something by normalization. Do I do it right? No. That is equal to that, right? So if you take this imaginary part, if I take this imaginary part, then we'll get eta over kn squared minus k naught squared plus eta squared. Right? If I take its imaginary part, introduce a little bit of loss and take its imaginary part. I can let the loss be very, very small. Okay, and then this will become a delta function again. And that gives rise to the local density of states that I had previously defined for you. But delta is not small if you have a lossy system. This is the real number. This is the real number. I can call this real number gamma. Okay, gamma. Call this number gamma. And what it says is that this is an eigenfunction expansion of this spectral Green's function with all real eigenvalues. This will be the eigenvalues of this system. Okay, if I plug this back in here. Okay, that will be the eigenvalues of the system which is always real. This is the real value function, so on. But what happens if I let eta becomes infinitesimally small in this system? If I let eta is, this is a function of eta, okay? If I let eta be very, very small, what becomes of that function? Does anybody know? You can sketch that function in your head, right? You can sketch that function in your head. If you just sketch this function as a function of k naught, when k naught hit kn squared, there will be a peak. It if I sketch this, and then the peak is proportional to, when k0 hits kn, the peak is 1 over eta. Right? This goes to 0. And then eta becomes smaller. This thing becomes narrower and taller. Narrower and taller. Actually, it is the delta function. In fact, you can prove that eta over x squared plus eta squared is delta x when eta goes to 0. Right? When eta goes to 0. So, according to my notes, it's phi. And you can always show that this thing must be equal to pi. You can always show that this is true, irrespective of what eta is. I was quite good at integration when I was young. Do you know how to integrate this?
Replace the variable.
What
Replace
variable?
x by cosine and
You know,
eta by
okay,
sine.
you're from China, maybe.
I learned this in Singapore.
You teach it in Singapore. What about Aditya? Do you know how to integrate this? How do you do it? What?
Wolfram always works.
What?
Wolfram.
We go to Wolfram for now. Okay. So I was afraid that the younger generation will not know how to do this. But I grew up in schools that were run by the UK system. So they taught us how to do integration really well in high school. Okay, so you do substitution. So if you went to Singapore to study, you study at Singapore, you should know how to do this, right? And if you study in India, you know how to do this, right? But if you grow up in this country, you might not know how to do this, right? You go to Wolfram for help.
I think that's what he's doing.
So, there are two ways to integrate this, actually. There are two ways to integrate this. One is to substitute with something. I remember that if you take the derivative of arctangent of x, it gives you something very complicated. When you integrate this, it gives you something that is similar to arctangent of x. And how do you integrate that thing? How do you differentiate that thing? Of course, you define y to be arctangent of x, and then you define x to be tan y. And then from this you find the x dy very easily, and from this you can find dy dx. And then you find that dy dx is actually something very similar to that. And then you can then integrate using this kind of property. But there's another cleverer way to integrate this, which is to notice that you know how to integrate this very easily. You know how to integrate this, right? This is equal to ln of x plus pi eta. This is equal to that. And so you can integrate this from minus infinity to a, for instance. You will go from minus infinity to a. And then if you write this in terms of real part and imaginary part, this would be x squared plus eta squared with the half in front plus the angle theta. Theta should be arctangent of eta over x, right? Something like that. But this is just the imaginary part of this. This one is just the imaginary part. So you take the imaginary part of this, you pick up this one. Okay, so this is a simpler way to integrate. Okay, another clever way, but simpler way to integrate.
I think if we use Cauchy integral, it will be much easier.
Cauchy integral?
Yeah, because the denominator we can write x plus I eta multiplied by x minus I eta.
A plus I eta. Then you do partial fraction.
No, just apply the Cauchy integral.
You have to do partial fraction, right? To get two poles and then pick up the poles.
Yeah, the pole is I eta.
Yeah.
Yeah, you can. You can pick up that pole here too, I guess. You're right. You could be right. I did not check your method. Okay, that you can also do this by Cauchy integration. Okay, so there are many ways to do this integration. Okay, and I'm glad that many of you know how to do this. So in the limit when this eta goes to 0, this becomes a delta function. And if I do things correctly, this actually becomes a delta function of kn squared minus k naught squared. Okay, with a pi. So this should become 2 pi, right? 2 pi. So this is equal to 2 pi kn fn k of r fn star k of r prime times delta kn squared minus k naught squared. In the case of the lossless case, in the case when we let eta go to 0, okay, and that looks almost like the local density of state functions that we have alluded to earlier, except that we have to do something about this delta function. This delta function let me just ignore the n for the time being, is k minus k naught, k plus k naught. And this has peaks at 2 points. So it has a peak here, k equal to k naught, k equal to minus k naught, right? So this actually is 2, no, delta k minus k naught plus delta k plus k naught. Okay, am I right about that?
There's a normalization factor.
Huh?
There should be a normalization factor. Right?
Yeah, you're correct. There should be a normalization factor. Let me see what the normalization factor is. According to my lecture notes I have here, it should be a normalization factor multiply, which is equal to 1 over 2k naught also. According to my note here. Tien, is that the correct normalization factor?
Maybe. I can't remember.
So let's try. So if we integrate dk delta k minus k naught, k plus k naught, about, say, in the vicinity of k naught minus delta k naught plus delta, you only will pick up this term over here, right? So this one in that vicinity is 2k naught. So this can be approximated by dk delta k minus k naught times 2k naught. Okay, in this vicinity. Okay, but we know this to be the fact. This has to be true. Like minus delta plus delta. This has to be true. So we have to normalize things so that this becomes x. Okay, this becomes x, and in order to make this become x, we also have to make this to become dx. So we plug in 2k naught there. And then we divide by 1 over 2k naught there. Okay, so everything in the parentheses, the braces, integrates to 1. Because I plug in 2k naught, this is essentially just dx, delta x kind of thing. Because I make this into x, this must be dx by putting k naught. So this must be 1 over 2k naught. So integrating this, give me 1 over 2k naught. Integrating this gives me 1 over 2k naught. Integrating this gives me 1 over 2k naught. Okay? Integrating this will give me 1 to 2k. So this normalization factor is correct. Very good. You're correct. There should be a normalization factor. And that is the normalization factor. Okay. So if we do this, then I can plug it back in and get something that looks like the local density function, but I had done something else also, which is that to express everything in terms of E, in terms of energy. Okay. E is h bar omega naught, and then Ek is h bar omega k. So what I did previously, when I did the derivation of the local density of states, looking at that from the quantum transport viewpoint, and this actually is h bar k naught c. This is h bar k c. Okay, so in order to change this into energy, I would have to write this as delta E minus Ek, and then I have to take out the normalization factor. If I have that 2k naught, since I changed variable here from k naught to h bar over c, I should multiply by h bar c in order to make this correct. Am I right here? Is it correct? Is the normalization factor correct? It's bar c. It's correct, right? Okay. Ken is checking for me, so I don't have to check myself. So right now I can replace this with that, and this is of no interest because k is never negative. K is never negative because k is e k squared is k dot k. No matter what k value you pick, this is always positive. K is never negative. So we can actually drop this part of the delta function and ignore them. And then when you plug this in into sum of the two and do the proper normalization, I get 2 pi, and then if I pick up these factors correctly over 2k naught, and then I will have sum over k n f of n kr f of n star kr prime delta E minus epsilon k. Okay, and actually I can put in my 2 polarizations in there as well. Okay. When this EKN for 1 and 2 are the same as each other, when n is 1 and 2 are the same, when n is equal to 3, this is 0. Okay. So if we don't count the 0 eigenvalues, we can ignore the 3, the longitudinal modes, and just count the transverse modes. And this is actually very similar to the local density of states. If we make r equals r prime, if I make r equals r prime, if I make r equal to r prime, then this is like what I had in the local density of states, but one very different thing that we should know that is different. What else do I need to do? The LDOS that I defined looks something like this. Okay, that was the definition of the LDOS. You integrate this LDOS dr over volume, you get DOS. This term becomes 1. But this is not quite that yet. Even if I make r equals r prime, it's not magnitude of the vector wave functions f. What do I need to do?
You need to project it onto.
What?
You need to project it onto some.
Yes, you need to project it onto something. But this is an outer product. to make an outer product into an inner product, what do you do? To make an outer product, F is an outer product. Because it's an outer product, it gives the matrix system. Okay, so this is actually in indentation notation Fi Fj. Okay, in index notation, that gives you a matrix system. I and j need not be the same in index notation. So how do I get this outer product to become an inner product?
Sandwich Fi.
Fi, that's one way, but what is a clever way to make this into an inner product?
Add the identity operator.
What?
Add the identity operator.
No, no. Maybe you know since you're a physicist. Xu Chen. What do I do to get this into an inner product?
Arbitrary vector.
What?
Arbitrary vector.
Arbitrary vector?
Use the arbitrary vector.
No.
No.
Can I just multiply by the delta ij?
No.
Would that transpose?
No. Okay, everybody got lost?
Wait, we got a few more guesses, right? Hold on, there's like two options, right? There's like expand and test, and then there's that thing, flip them around like that. Transpose maybe? I don't know. All right, I'm out of guesses, I don't know.
Okay.
Could it be a trace?
Oh, very good. Trace. Take this trace. Take the trace of this matrix operator and it becomes an inner product, right? What do you do when you take this trace? You make I equals j and sum them up. Okay? So the trace of a matrix Aij is sum of ai, I is equal to 1 to n. This is how you take a trace of a matrix system. Right? So we have this outer product, we take its trace. So trace of Fi Fj is sum of Fi Fi. Okay, take its trace. And trace is independent of basis if you have learned your matrix algebra well. It doesn't matter what basis you define it in. You can project onto other bases and get the trace, but you don't have to do it in a long-winded manner. Okay, so that is it. So we need to take the trace of this thing to make it become like that. Okay, so if you take the trace of A and then make R equal to R prime, okay, then this thing here becomes an inner product. And then you would have, let me see, pi h bar c over k naught square, right? K naught, no k naught square. And then you can sum k n k r square. The trace of that becomes the inner product. And then delta E minus E k n. And that is just the local density of states. So if you have the dialectic Green's function, you find the spectral Green's function by taking the imaginary part of the dialectic Green's function. Make R equals to R prime, take its trace, that gives you the local density of states. Okay. Gives you the local density of states. So I thought this is elegant. I don't know why it happens this way, but it's elegant. It's a piece of knowledge that you should know.
Well, does the dimension agree for your?
Did I make some mistakes?
The dimensions doesn't seem to agree.
Why don't we agree?
You have a h bar and c over k naught and you have.
This comes out of those normalizations that we did, right?
Right. What's the dimension of h bar c over k?
I know HKC is energy, so it's if I put a K naught here,
This is like
put a K naught square
you
here,
have a dimension of.
this is energy.
Yeah.
So it's energy over K naught square. This is the dimension of this. Is this wrong?
But I mean, I just your local density state up there that's
This is dimensionless, right?
Yeah.
This has been normalized.
yeah.
Actually has dimension of 1 over v. This is the definition of the local density of states. But this is the spectral Green's function, so this should have dimension of the Dada Green's function. What is the dimension of Dada Green's function? We had the Dada Green's function somewhere, right? Erased from the blackboard. It's 1 over k naught squared, right?
Yeah.
So it's energy over k naught squared. This has a dimension of 1 over energy. So the energy cancel each other. The whole thing has dimension of k naught squared. So dimensionally is still correct. So 10 is good. You give me all the normalization factors. Correct.
But up there you have when you define your local density state,
Yeah, this has a dimension of 1 over energy.
yeah.
So you integrate this over energy, you get a number of states. This becomes dimensionless after you integrate over energy. Okay, so if you integrate this over energy, it becomes a number of states per unit energy input. Okay. So let's see, we have some time left. So with this spectral Green's function, this is what happens. And this can be related to the local density of states quite nicely. Okay. But then, there's something else that you can do. You can relate this to quantum mechanics. These are all classical derivations so far. Okay. These are all classical derivations so far. We have not related to quantum stuff at all. Okay. So now think of this as a classical system. Well, this classical system is in time harmonic motion. Every part of it is in time harmonic motion. Each part of that can be thought of as a quantum harmonic oscillator. And we can quantize each of these harmonic oscillators that we see in this classical system. And then we can associate an energy with each of these states, which is a quantum harmonic oscillator. It turns out that the energy that is associated with a state is something called kBT, or half kBT. This is from classical thermodynamics. That if you have a system with a certain degree of freedom, the energy that is given to that degree of freedom is half kBT. We learned this in high school physics. It's called the equal partition energy theorem. Okay, we learned that in the idea of gas law, Boyle's law, and other kind of thing. Okay. It turns out that for a harmonic oscillator, you give it 2 degrees of freedom because it has kinetic energy as well as potential energy. So each harmonic oscillator will pick up kBT of energy. So if this harmonic oscillators that we have in the system is in thermal equilibrium, which it is because it's only in thermal equilibrium that we can define this spectral Green's function. And each of the harmonic oscillators will pick up that amount of energy. So for a harmonic oscillator, this number is kBT. Okay? And we can also learn them in classical physics before quantum physics came about. But then, when quantum physics comes about, something more complicated happens. Photons are quantized, harmonic oscillators are quantized. They cannot have infinitely divisible energy. So this formula gets a little bit more complicated. It becomes something like this. If you have a simple harmonic oscillator, if you take into account of its quantum effect, then this should be the energy given to each harmonic oscillator according to a number of workers first term here is actually due to Planck. Planck actually just guessed this factor. He guessed that since he couldn't match the black body radiation law, he has to come up with a function that will match it. So he assumes that all the harmonic oscillators that he has that are oscillating are quantized. And if you use thermodynamics argument and then Boltzmann's law and that kind of thing, he comes up with this formula. So this formula is actually a simple factor. You can rewrite this formula. You can rewrite that part of Planck's distribution as the sum of this. You can write it as this, or maybe just like this. And expand this as a power series, and then if I expand this as a power series, I have that. And this is just Boltzmann's law, the Boltzmann's law that if something has this kind of energy, the likelihood of finding a particle in that state is proportional to that constant, which means that high energy states are less likely to be filled than low energy states. So if you think of this harmonic oscillators at quantized energy level, the high energy levels are less likely to be filled compared to the low energy level, and then the photons themselves will distribute themselves in different states, in the quantum states. And then you come up with this formula according to Boltzmann's law, and then multiply each photon state by the energy they have and the probability that they would be in that state, you come up with that formula.